Hi, thank you for having me. I have to say that it's twice an honor because it's an honor to be here. It's an honor to have been Chankar's student. And you see, we all have our pieces of knowledge that we got from Chankar that have no relationship with academia, right? So coming back to Chankar's quotes, this is something that Chankar said to our group when it was around 2008. I don't remember the exact date. It used to be join the Navy and see the world, and now it's become a grad student and see the world, right? So we have conferences all over the place. So the story goes as Chankar takes a sabbatical in Stockholm, right, in KTH Zurich. And CPS Week is in KTH Zurich in April 2010. So we all submit papers. And pretty much all of us get our papers accepted. It was an amazing conference, right? It was one of my first real conference experience where I'm sitting there surrounded with brilliant people, right? And so we're all there. And then the conference goes from Monday workshop, and then until Friday, the conference is over. And then on Thursday, we have a volcano, right? So Iceland volcano explodes, and then Vulcan panicking. All flights are canceled. And our hotel says, well, ash cloud, you know? We're all stuck. We have to do something. And then what did we do? So we decided, well, since we're in Stockholm, which airport is open? And the options were Madrid, Sicily, and I think some airport in Turkey. And we said, OK, let's go to Madrid. So it turns out that being Chankar's student has some perks, right? And one of those perks is that sometimes Chankar would say, or in this particular case, it was Gary Givens who was working for Chankar, right? Guys, you need to get out of there. Just do it. And we did it. We rented a car, and we did exactly that trip. And we didn't rent any car. We rented an Audi. So this is the gang. So the gang is me, Andrew, who's in his startup now, Ram and Branko, who are not present here, but at Washington University, and Sam, who has an upside-down picture in University of Washington. So you can see that it was a very successful trip, right? Like, we actually get a lot out of it. Those are pictures from the trip. We got to play guitar, eat tapas, drive through the longest bridge in the world, right? And this was really one of the best moments of the trip. So we came back to Berkeley, and we had bags full of receipts, right? And we had to do the reimbursement. And this is an awful picture because it's all pixelated. But you can see that we have that the screen died for some reason, which I don't know why. Oh, there you go. So as you can see, we have piles of receipts to do the reimbursement. So I know that this doesn't involve any pictures of Chankar because he wasn't in the car with us, right? So he stayed at KTH. But like, one of the things that I'm really grateful to have experienced here at Berkeley was this trip. It sounds like we had a really long vacation, and it actually was. But I actually learned a lot out of it. And we got to interact a lot during the trip, right? So it was 5 days stuck in a car. So you actually get to talk about all sorts of things. So OK, now I'm going to actually give my real talk. What I try to do here is to condense, I don't know why this is moving. I try to condense most of the work that I've been done in hybrid systems in the past couple of years while being at Washington University. So this is going to be like a rough overview. So stop me at any point if I don't sound like that I'm making sense. So I'm going to start with switch systems. So this is the end of my thesis here at Berkeley. So you have a switch system, and then you have a discrete input, right? And the input is 1, 2, 3, 4, 5, right? And it turns out that this is completely equivalent to writing a convex combination of all of the vector fields. So you get these lambdas, and lambda gets to be either 1 or 0, so you don't get to choose anything in the middle, right? And the equivalency is quite obvious. So if you choose your discrete input as j, then that means that you have a vector with m components, and then the jth component is equal to 1, right? So this is super useful. It turns out that you can immediately from this formula, you say, well, I mean 0 or 1, so why don't we allow this? Why don't we relax this? And we start solving problems in the relaxed way. So it becomes, it's not, I mean, if you solve it as a convex optimization problem, it's not quite a convex problem, right? But it has a lot of really nice properties that you can start dealing with. So we're going to call some executions the ones that have lambda either 1 or 0 as pure, and the other ones as relaxed, right? And it turns out that if you go through the literature, you'll see, if I can get rid of this. No, I couldn't get rid of that. It doesn't matter. So if you go through the literature, it turns out that Berkovits in 1974 proved that the sets of pure and relaxed solutions are identical. So it turns out that it's obvious that if you have a pure solution, it's also a relaxed solution, right? But if you have a relaxed solution and then the lambdas are 1/2, 1/2, then what does that mean? And then Berkovits said in the chattering lemma, oh, it turns out that there is a pure solution that will give you exactly the same result. And then the question is, well, which one is that solution? So the typical example is suppose that you have a plane, so it's moving forward, but it can only turn right or turn left, and you want the plane to go straight ahead. So we all know that the optimal solution in that case is you just jitter all the time. You keep switching, right? So you get chattering. So this result was out there for decades, right? So it was known by Hager as relaxed controls. And everybody knew that these were the same results. But once you have the relaxed solution, so what do you do with it? So we came up with a way of actually projecting relaxed solutions back into pure solutions. So we came up with a way of coming up with the chattering. But we came up with a way that it's actually numerically feasible. So the idea goes as follows. So this is your relaxed solution. It goes between 0 and 1, and it theoretically practically doesn't make any sense, right? It only makes sense theoretically. So then step 1, you choose a discretization, and then you take a wavelet transform. And in particular, you take the hard wavelet. So you're taking averages within each one of these windows, right? So then after you have that, then you take a PWM transform. And then you get a pure solution back. And the PWM, this is basically the PWM modulation of the hard wavelet. So thinking like in the op-amp technique, right? So you draw a triangle and then you compare. So this is really a comparison between the triangle and this line. And with this, you actually get a solution which we're going to call lambda pure. So you give me a solution that's relaxed, you get back a solution that's pure, right? So this is the theorem. The theorem says, well, take your relaxed solution, and then you get your fake trajectory, a trajectory that it's not implementable because it's telling you do 1/2, 1/2, right? Now compute the pure trajectory that you get out of our technique. And it turns out that they converge. So this is a constant. This is the bounded variation. I'm not going to go into details for this, but this is basically all constant in n, and then it decreases with n. So what we basically get is, so all you have to do is to compute all of your results with relaxed solutions. And then you just apply one of these techniques. You could use ours. You could use another one, because no one is saying that our pure solution is unique, right? And you're going to get very, very nice convergence results. So the way we used this in our Scicon papers was we said, well, so why don't we actually come up with an optimal control algorithm? So the optimal control algorithm is, so choose an arbitrary discretization grid. So you have a continuous time system. And here I have to stop for a second and say, well, most people, the way they solve these problems is that you have a continuous system, and then step 1, you discretize, and then you solve everything else after it's discretized. And that's a mistake in this particular case, because in the discretization is the information that you want to play with. So what we are doing here is that we're not only iterating over the control, we're also iterating over the discretization. So step 1, you choose a discretization. You compute your descent direction in any way that you like. Well, you have to satisfy some conditions, but the technicalities are not that relevant. Then you compute your step size, and then you project back. And that projection, so when you take the wavelet transform, the PWM, gives you a new discretization, which is induced by the PWM. So every single switch of the PWM will tell you, oh, this is your new discretization step. You iterate this, and you actually get a very nicely convergent, super nice properties result, right? All of the results are in the paper, right? So this is a table that I took from the paper. So we ran this in 4 different examples. We took the best mixed integer programming implementation that we could find. So this is involving a Groovy solver that had the best benchmarks on a popular paper, right? And as you can see, we ran, so this is a quadrotor helicopter with 4 switch modes. This is a water tank. I think this is a standard benchmark of the water tank with 2 tanks, right? This is a typical QR, and this is a flexible needle, which was at the time our favorite example, right? So this is a needle that you can either push or rotate, so you have 2 switch modes, and you want to avoid obstacles. So all of this is compatible with constraint optimization. So you can do this, basically add nonlinear constraints on the state and the typical constraints in the inputs, and it will work anyway. And as you can see, the computation times are orders of magnitude faster, because we're not doing any mixed integer anymore. Everything is done with gradients. It just so happens that we know how to go from those relaxed solutions to the pure solutions in a very clever way. Right? So now the question is, so where does this take us? So I was having a meeting with an undergrad student at WatU, Tyler, who's actually coming to Berkeley now. Yeah. So he's really excited about coming here. And I was describing these results to him, right? And one day he says, well, but you see, the problem with your switching formulation with this HiCom paper is that you can switch anywhere, and we all know that that's not true, right? So you're going to have certain regions in space where you're not allowed to take one switch or the other. And I said, well, I mean, we could work on that. And then probably like 30 minutes later, he said, well, but why don't you use a complementary condition? So you multiply lambda times the domain, right? So if you have a domain that has to be negative, and you just multiply lambda times it, so then if you're outside the domain, because of this condition, lambda has to be 0, right? This is really simple, right? And it turns out that this is a really powerful idea, because this is a generalization of sliding modes. So in the typical case of sliding modes, you just choose that function d as one complement the other, right? And you take one, the boundary is basically, you're knocking out one dimension. But now you can make them intersect. So we said, well, I mean, what do we get with that? And so this is a very, very simple example. So this is a system with constant vector field, 2 modes, no continuous input, right? So you have one mode that goes from this line below, and it's a mode that points up, and then another mode that goes from the green line up, and it's a mode that points down, right? So when you start this problem, then of course you have to stay in one mode. But as soon as you hit this boundary, oh, and what you're trying to minimize is basically move as further to the right as possible. As soon as you hit that boundary, then the mixing between both modes starts following the boundary, and then you go around 1/2, and then it starts following the other boundary. And all of this is very, very transparent, right? And this is the relaxed solution. This is what happens when you take the PWM solution, and this is the approximation, and this is for n equals to 5. As you can see, we're actually computing way more points on the relaxed solution than on the PWM solution. The typical fear about all of these chattering solutions is that everybody says, well, you're going to have to chatter a lot. It turns out that if you choose your chattering in a proper way, you don't have to chatter that much. You see? Remember, the convergence result that we have is 1 over square root of 2 to the power of n. So as soon as n is significantly large, like 5, 6, 7, like this thing is converging almost exactly. We can also do the typical, so this is the classical Branicki example, where you have 2 linear systems here and here, and another 2 linear systems here and here. In this particular case, we actually added a control input, continuous control input, right? And there's no overlap between the modes. And this would be usually a challenging problem to write into your optimal control formulation. But this is the type of problem that we just threw into a solver without even thinking. We just wrote the right constraints, and then you get the right result, right? We're trying to minimize to 0. And this is another one of my favorite examples. So this is a quadrotor helicopter with several modes. In this particular case, what we were comparing was the way you do obstacle avoidance in this type of problems. Usually you add constraints. And as all of the people who work in numerical methods know, like every single constraint you pay its price in gold, right? Every single constraint that you add, and your solver is way, way slower. So what we did here was, well, why don't we create costs that change with the mode? And then we're going to create a mode which is defined by a particular region, where we say, well, in this mode, you're going to pay a gigantic cost, no constraints. You get this relaxed solution. Then these are the projections. And as you can see, you don't always get a really good projection, right? So in this particular case, we had to crank up n to 9, I think. And these are the relaxed weights, right? So this is a really nice result. And then we were wondering, well, like, where is this going to take us, right? So can we actually take this result out of the realm of switch systems and start working on problems where we all know that this should be possible. We all know that hybrid systems should give you the solution, but we don't ever we don't usually have the algorithm to actually do this. So we said, well, let's suppose we have an apartment. This is actually a real apartment in the St. Louis area. So there are 2 bedrooms. This is a bathroom. And this is a big area, which is a living room and dining room, right? So there is 1 HVAC system and 3 thermostats. And what we're assuming basically is that the thermostat measures an average of the temperature around a certain area, right? The HVAC system is an absolutely obvious HVAC system. So it has fan control, which is kind of reasonable in the St. Louis area where the weather is awful. And it can go AC or heater, right? And then we say, well, if you really want to save energy in this particular apartment, then what you have to do is to do zone control, right? I mean, everybody knows that. You talk to architects, and that they're going to tell you, well, that's really what's coming, right? And how do you define those zones, and then how do you model them? So then we said, well, why don't we divide the zones by the doors? So if the door is open or closed, that's going to make a huge impact on your energy usage, right? So we modeled this as a switch system where the doors would change, but then we threw PDEs on top of it. So these are the 2 PDEs. I'm not going to go into all the details, but what are the things that matter here? So you have only 1 derivative on the temperature. The Navier-Stokes equation is stationary. And this is both for practical reasons, because otherwise the problem is really gigantic. And number 2, because stationary Navier-Stokes equation have really nice theoretical properties, so you can prove existence, uniqueness, etc. And then when you move the doors, you really change only these 2 parameters. So this one is the thermal conductivity. So when the door is closed, then you don't have so much flow of heat right between the rooms. And this one is a parameter that basically models friction on the airflow. So when you close the door, this value alpha, which we're choosing right now something like 10,000. And that will force you to go to 0. So instead of writing the Navier-Stokes equation only in the air, we write it all over the place. And we just say, well, the walls are like very, very big dampers, right? And then we run this algorithm where we say, well, we're going to relax the thetas. And then we're going to try to identify, just by looking at the 3 thermostats, whether the doors are open or closed. So this is the average error of our estimation, where G is our gradient method, and B is a common algorithm, which I didn't write in the slide. So this comes from a paper by Bahari. It's basically a probabilistic method. It's what you would expect if you were doing Bayesian estimation. So you say, well, I'm going to simulate every single combination of all the doors, and I'm going to compare that, or the expected value of that, with respect to what I'm seeing. And then with that, I'm going to choose the optimal theta, given a Dirichlet distribution, right? So what we get here is that this one is the error on the initial temperature estimation, which I didn't write here either, sorry. As you can see, our algorithm makes a really nice estimation of the initial temperature, but this is the interesting one. So this is the estimation of the error of the door estimation, right? So we have 4 doors, so basically 0.25 means that you always get 1 door wrong. And what this means is that just by looking at 3 thermostats, you can actually get information about not only the configuration of your apartment, doors. You could do exactly the same with windows. We didn't add windows because it was a little bit too much, but the formulation is exactly the same. But also, you can also guess where people is standing inside the house, right? And you can get that because you can actually guess the initial condition. So we wanted to estimate the thetas, right? But we can also estimate the initial distribution, which is going to be very useful if you want to do MPC, for example. So this is the initial distribution that the apartment had. This is the error that the probabilistic method gets. And this is the error that we get. So we are 1 order of magnitude better than any probabilistic method. And the interesting thing, right, so this is where we stopped and we said, well, but why are our results so good? Because it really didn't make a lot of sense. I was hoping that it was going to be more of a match, right? And my guess is that by taking the combination of the outputs of the system, as opposed to the combination of the inputs of the system and see what output it produces. You see, if your system is completely linear, then you're going to get exactly the same, right? But when you have high nonlinearities, actually the nonlinearity is giving you the extra information that you cannot get from just looking at the outputs. You see, so we're actually benefiting from the fact that the Navier-Stokes equation is awfully hard to solve. In terms of numerical calculations, since we are using standard gradient-based methods, our memory usage, so you see we're doing finite elements, we're doing a lot of things like behind the scenes here. So the amount of memory that our algorithm uses is something to the tune of like 2 gigs of RAM all the time. But the probabilistic method, the skies rocket right away. So if you're wondering why we didn't use Windows, it's because by n = 5, the probabilistic method just wouldn't even run in our server with 100 gigs of RAM, right? And in terms of computation time, this is taking about 20 minutes. And we're not doing any magic with the algorithm. So if we wanted to make it run fast, right, we could make it in the tune of 2 minutes. So this is really a tool where you can just get the information from your thermostats. And because you're using that information in the right way, because you're thinking of the switch system in the right framework, right, then you can estimate doors, you can estimate initial conditions. And I mean, I'm not going to even go to the privacy considerations that, of course, Roy and Lily are way better than I am. But the fact that people can guess where you are just by looking at your thermostat without even trying, right? So this is not even using some fancy deaggregator or anything. It's kind of like scary. So that's all I have. Feliz cumpleaños, Shankar.